Hello, my name is Bruno Mesnay. I'm part of the EMEA Accelerator team based in Montpellier, and I would like to take less than 10 minutes of your time to show you how an accelerator can help you boosting your software application, especially when it is dealing with real-time processing. This is a demo developed by Xilinx Research in Dublin and ported to our Montpellier server. Let's do a real-time rescaling of a video, enlarging the width, and see how it works using a full software configuration method and using a CAPI hardware accelerator. To rescale the image, we use a polyphase algorithm, which is an interpolation method taking input pixels to calculate the output pixels. So let's see first the environment built for this demo. Let's consider a video with a WMV format. We take this format as an example, but it could be any other standard. The video file enters FFmpeg, an open source video library, being scaled up or down to a specific resolution by a dedicated scaler, and the results are written into a video stream feed1.ffm. The video stream is used to feed the streaming broadcasting server, named ffserver, to be distributed to multiple clients over HTTP for viewing. At the end of the line, the video player, which will display the video read through the network. This architecture allows us to do all the video processing in an IBM Power 8 server and remotely displays the scaling result on a laptop. All these FFmpeg and ffserver are fully configurable and allows us to test any configuration. For your information, and just to give you an idea of the size of the data we are working with, we will use input and output images that, once fully uncompressed, will generate a bandwidth around 1 gigabit per second to and from the scaler. Let's see now what the FFmpeg scaler process looks like and how the benchmark comparison is done. The video file enters the FFmpeg, which will first demux the input file and get the packets containing the encoded data. These encoded packets are then passed to the decoder, who will produce an uncompressed raw video. The mixer will then extract bytes from 3 colors RGB arrays and rearrange them into one array before passing it to the scaler. The scaler will do the video format conversion, and after the scaling, the frames are passed to the demixer, which converts back to the colors to RGB, and then to the encoder, which encodes them and outputs encoded packets. Finally, those are passed to the muxer, which writes the encoded packets to the output file or the feed stream. As you may guess, the most computation-intensive process is the scaler, and this is the one we will move to the hardware later. We will run the following command line, which contains the -RE option to read the file at the video frame rate. And as you can see, we use the Xilinx software flag and send the results to the feed stream. Now, let's see how this works in real time. On bottom left, we first start the FF server so that we can send to the viewer everything that is read and converted. On bottom right, we then start the FFmpeg scaler process with the command we just saw with the Xilinx software flag. And we start the video player to see the result. In the bottom window, we can see the statistics associated to that conversion. They show an average rate of 2.2 to 2.3 frames per second. You can notice that video player generates some buffering, but this reflects the time that the scaler takes to do its processing. From time to time, when the buffer has been filled, the video player releases the frame converted, and we can see them displayed. I think you got it, no need to wait for the end of the movie. With the 2 frames per second, the 30 seconds movie will take 7 minutes and 4 seconds to be converted. Now let's see if hardware can do better. We will keep the exact same processing and just move the scaler in a Xilinx Vertex 7 FPGA. We will then add all interfaces components such as PSN and PCI Express needed to discuss with the scaler in the FPGA. In the case of the FPGA implemented scaler, the host, meaning FFmpeg, will communicate with the FPGA with coherent shared host memory. That is, all scaling parameters will be sent in the shared system memory, and then all frames, one after the other, are sent into memory, and the FPGA will process them when ready, and then send them back to the shared memory. Now, let's see if the FPGA really helps the processing. Same then for software. On bottom left, we first start the FF server, and on bottom right, we start the FFmpeg scaler process using the same command, but with the Xilinx hardware flag. And we start the video player to see the result. As you can see, with the scaler moved to the FPGA, we are now able to do real-time scaling processing, keeping the same definition than the original movie. The statistics associated to that conversion shows an average rate of 30 frames per second, which is exactly the video rate. And this time, let's wait for the end of the 903 frames processing. Now let's summarize how the implementation was done and why CAPI helped it. So we have on the left the application running on the Power 8, and on the right the scaler program running in the FPGA. In the middle, the shared system memory, physically in the P8, which will be used to exchange data between them. First of all parameters needed for the conversion will be shared in memory through what we call the work element descriptor, or WED. Then two different memory zones will be used to share the frame to convert and the frame converted. To share the status of these two frame buffers, we use the specific status word contained in the work element descriptor, which can inform the application and the FPGA if buffers are full or empty. We could also have used MMIO access to manage these controls instead of the status word. As you see, this coherent shared memory architecture is very simple and really helps the application programming. I would like to add a very important point that may make the difference. In this demo, the Video Scaler accelerator has been completely developed in C++ and then synthesized by the Xilinx Vivado HLS tool to generate the RTL code. No RTL coding was needed. I'm sure software designers will appreciate to code in C or C++ the FPGA program. Now, let's see what CAPI brings to the demo if we compare it to a full software solution or a standard FPGA accelerator. First point, as we just started to highlight it, is the ease for programming. We all know that inserting hardware in the middle of an existing application can bring some complexity, but as CAPI is delivered with the PSL simulation engine, which simulates all the CAPI part, the programmer can very easily debug his application and the FPGA program before trying it on a real hardware. All hardware designers will surely understand the importance of this feature. The second point is the hardware acceleration. We saw the result. This is awesome. We are able to do real-time processing thanks to the FPGA technology, which means that we have been able to improve the processing speed by a factor of 14. The following points are about the way we can reduce the CPU usage, thanks to the FPGA, but also thanks to CAPI, who get rid of the software driver and avoid any associated data copy. Look at the numbers. A 30 seconds video, we saved 8 times the CPU time. And at last, looking to the memory saved by not using a driver, we saved 6 times the memory used. Are you convinced by what can bring you a hardware accelerator to your application by just offloading some processing? We are building or installing plenty of other demos on our Montpellier servers so that you can test them by your own. Don't hesitate, contact today the Montpellier Accelerator Center, Alexander or Bruno. You will get all answers to your question and even more. Thanks a lot for your time, and I wish we will be able to help you very shortly. Thank you.